Welcome back to the lighting videos. In this video we're going to add a simple light to the scene, and we're also going to talk about materials. So let's get started. So we're back in main, and since the last video, video 9, where we did the mesh, I have made some small changes in here, added some comments, commenting to functions, that kind of thing. The full source code will be available in the uploads area, the code listing area. So, but if you are following along, you can pretty much start where we left off the last time. I'll point out some of the changes. So I have added, I've added two models, a bowling pin and a bunny. These are the positions for the bunny and the bowling pin, and I moved the crates a little bit, so you might notice the different positions. The scale for the bowling pin and the bunny also has been added. So we now have 6 models. So here's the bowling pin object file and the bunny, and they both have textures. I also added a light. So our light is a simple sphere. So it's an OBJ object, which is literally a sphere that I created very quickly in 3ds Max, and we'll deal with that in a little bit. Okay, so let's deal with that light in a minute. I'll actually just do it right now. So let's add a position for our light. Back 3, and we'll call it light pos, and we'll give it an initial position of 0. What do I have here? I'm looking at my notes. 1 and 10. So it'll be 10 units back and 1 unit up in the air. And let's give it a color, and I'll be talking about what this means in a little bit. So we're just going to make it bright white, which is 111. And just do something interesting, let's move our light, and I need to give it an angle. So I need to add an angle up here. Let's put one right here. Initialize it to 0. Let's move the angle based on delta time, and we'll move it, I don't know, 50 units, a speed of 50, whatever that means. Kind of play around with the value. So we're going to move it back and forth in X, and I'll explain what this is in a second. We're going to use a sine wave just to make it interesting, and make sure to remember our angle has to be, when we're passing it to the sine function, needs to be in radians. So we're going to slide back and forth basically, and our offset position, or the position that it'll go to, the max positions either side will be 8 units. Okay, let's render our light. So here we're going through a loop and rendering the scene. If you remember, we did that last time. Now we have 6 models instead of 4. So let's render the light. So we want to move the light, so we need to, our shader expects a world position. So we're going to set up the matrix that we pass, the uniform that we pass to the Vertex Shader. Passing it, so we're going to use the GLM translate, remember doing that before, and we're passing it the position that we just set up here. So we're basically keeping the light position at 0, 1, so 1, 0 in X, 1 in Y, and 10 back in Z, but we are going to mess with X, so we're changing X. So we're setting up, creating our model matrix, and need to do something here. Light shader, what is that? We need to add a light shader. So up here, let's copy this information, these 2 lines, and we're going to use, so we're now going to have 2 shaders, one for the lighting and one for our light. There's two different things. We'll get into that. So right now we only have one shader. So let's come over here to the project and let's add. So I've already, behind the scenes, I've already created the shader files for the lighting. And where are you? Right here, lighting frag and lighting vert. And if we go into, let's open up the basic vert. This is the same Vertex Shader. I think I might have organized this slightly since the last video, but it's basically the same shader. So our lighting vert is the exact same thing. So these are just copies, and our basic Fragment Shader, the lighting is the same thing. So nothing new there. But I want to have two shaders. So back over here, we're going to load our basic like we were doing before, and we're also now going to load our, we're going to create a shader for lighting. And we're going to be writing the code for the lighting shader. So let's call this lighting program, and we'll call this the light program. And so we need to okay, copy the name here. So we're loading two shaders. One that's called the light, which is basically just going to help us render the light geometry itself. And then we want a lighting shader. And so we're going to call it lighting program. Actually, let's just call it lighting shader. So this is our lighting shader. And we probably messed some things up down here. So we're going to copy that name, lighting shader. This is going to be our general shader now. So what we called before shader program will be now the lighting shader. So we're going to change that name. And so wherever shader program is, we're going to change the name. Okay, so then our light shader, what did I call it? We're going to use our light, let's call it light shader. This is the shader not for the lighting, but for the actual light, the light bulb. Let's copy that. And this is paste. Okay. So this is our light shader. It's going to move our light back in the scene back and forth. Okay, so remember, you got to use first, you got to activate the shader. Then we want to set some uniforms. So we want to set the light color, light color, and light shader, set uniform. We want to set just like we do with our normal shaders, we have to set the model, the view, and the projection. So I'm going to copy this line. This will be our view matrix, and our projection matrix. Then we need to draw, what did I call it? Light mesh. Then we need to draw our light mesh. Okay, so let's build just to see if we're somewhere in the ballpark and run it. So F5. And if you can see there in the console window, okay, so, it loaded our now 6 meshes, and it looks very crazy. So now remember what we just did in the mesh class, we added a third parameter, a third attribute, and so we need to deal with that. So that's why the texturing is kind of strange. But you can see our little bunny and our bowling pin sort of is there. So let's fix that. So let's close. Let's open up our lighting shader, because this is what we're using now for our the shader that our models, all of our models are going to be using the lighting shader, and the light shader is what our little sphere that represents the light bulb is going to be using. So let's open up our lighting Vertex Shader, and add our, remember we added a normal, so our OBJ files now need to contain a normal. So let's handle the normal in here. We'll just call it normal, and make sure to change the attribute location for the texture coordinate to 2. So the order that we dictated was, we said the positions could be first, normal, and then the texture coordinates. So that's all we need. Let's go ahead and change it in the basic vert as well. In fact, just to be easy, let's just copy these 2 lines. Oh, 3, why not? Even though we didn't change the first one. Save, run. Oh, cool, lots of problems. What did I miss? Oh, I missed typing it correctly. So that should be an equals. I made it a minus sign. So let's go into our vertex, or our lighting vertex shader, and change that. That's what happens when you type too quickly. So save, come in here, save, and now let's run it. So it's loading the models. Okay, so here we go. So the scene is what we saw before, except with now the addition of our bunny, which looks very bland, and our bowling pin. And the crates are moved out a little bit to the side. So it's basically the same scene. Oh, there's our light. Okay. I was trying to move back far enough to show you the light. So that's our little light. It's showing up in black because we haven't dealt with the shader yet. We need to, let's go ahead and fix that now. So in our basic, which I probably should, I don't know, this is just for the sake of this example, for this tutorial, this probably should be labeled something different, like light or something like that. But I'm just keeping the name the same. So the Vertex Shader is fine. I need to open up the Fragment Shader for our light. And our light is actually not textured. Actually, sorry, I take that back. It is, but we're not going to worry about that. I don't want to use the texture coordinate, even though we're passing it. We are passing it over, but I'm just going to ignore it because I don't need it. But what I do want to do is use the uniform that we set up in our main program, and we called it light color. Make sure you name it correctly. Light color. Lowercase l, uppercase c. We have to make sure the name is the same. All right, so we're bringing in our light color and setting it, and let's go ahead and just set our color of our light to be that color. And we're bringing in a vec3. Probably could have done a vec4, but we're bringing in a vec3 and then just setting the last component, which is the alpha, to a 1. So save that, and everything else looks to be the same. And now let's run it. Okay, let's back up and see if our light looks the same or looks better. Okay, so our light now looks right. So it's a white color. If you want to change it, we can go back into main, and you can pick whatever color you want. So if you want it to be yellow, you can remember. Colors are R, G, and B, so red, green, blue. So if you get rid of the blue, make it a 0, and compile. So then run it. Our light should now be yellow. Okay, there we go. Now we got a yellow light. But the scene's still flat. It's not doing anything. So we need to now talk about our lighting shader. Okay, so let's open up our lighting vertex shader. This looks fine at this point. What we're going to do is add the components of our lighting that we talked about: ambient, diffuse, and specular. And we're going to add it in that order. For ambient, we don't need to make any changes in here. So let's open up our fragment. We do need to make some changes, actually quite a few in here. So let's add our vectors, our colors, ambient, and we're gonna set this as, Actually, before we do that, I need to add what I'm calling a ambient factor. And I'll explain what this is in a minute. Light color times, so ambient is going to be the color of our light times our ambient factor. Since I'm not introducing materials yet, we'll get into materials in a minute. We're just going to create this fictitious thing, this variable called an ambient factor, which is basically setting, multiplying our light color by some factor, which is representing the intensity. So you can consider this our ambient intensity. When we get into materials and the different components that make up the light's color, this shader will get a little more complicated. So we need to add let's call this our ambient. We need our diffuse component, and we need our specular component. Our diffuse is going to be a vec3 diffuse, and until we get there, we're just going to say that this color component is 0. So what we're doing here now is we're defining the Phong lighting model in our shader. So we'll just deal with ambient first. So diffuse will not have any properties yet, and as well as our specular, and then we'll build these as we go. Now there's a constructor. If you notice, I'm not adding 3 parameters because this is a vec3. There is a GLSL constructor for a vec3 that can take 1 parameter. So it assigns all 3 components, XYZ or RGB, to this value. So this is 000, and this is also 000. So our frag color will be the color. Let's move this. Let's call this vec4. Let's call it our texel, and that will be our sampling of our texture. And so the final color will be a vec4, and it will be the combination of all 3 colors. If you remember back in the slides, I said that the color that Phong lighting combines 4 color components, but we're only worrying about 3. Ambient, diffuse, and specular. We're not going to be dealing with emit in this tutorial. Okay, so that's it. So basically we're setting the ambient to the light's color times some intensity factor. We're setting diffuse and specular to 0. So these 2 components here will be 0. So our final color will simply be the ambient value multiplied times our texel. Alright, so we need to add the uniform for that light color. Whoops. So it's a vec3, and we called it light color. Let me go back over here to make sure. So for our, we're going to use the same color actually for our light shader. So we're going to need to do this same thing. We're going to need to set the uniform of this shader to the light color. So the lighting shader also needs to set the light color. And let's go back to the Fragment Shader. So our light color, so this needs to match this. So our color is coming from our application. So now, if we run this, we should only have our ambient component of our Phong lighting model. Okay, so it's yellow, so notice that the ambient of our scene right now is slightly yellowish. I'm going to change that actually and put it back to white. Rebuild. So we're saying that our light has an ambient was yellow, now it's back to white. So the background up there, the sky, if you will, we don't really have a sky, so the background that we're drawing in is the same background color that we've been drawing in, so that's not going to be affected by our lighting. The only thing affected by our lighting now is our 6 models, which includes the floor. This, our light model, has its own shader, so that's why it's moving back and forth in bright white. So let's add diffuse. So now diffuse, if you remember the slide I showed before, it takes in consideration the light position, the light vector, and the normal vector of the surface. And so we need to add that now. So let's go to our lighting vertex shader and make some changes there. So we're going to pass our normal vector out through the vertex shader to our fragment shader, and we also need something. We also need the position of the vertex, but we need it in a different space. We need it in world space. That will be used shortly. I'll show you in the fragment shader to come up with our lighting position. So, all right. So we're passing these out. So let's go ahead and pass them out. Normal with a capital equals normal, which is what we're passing in as an attribute. Frag position is going to be our in world position now, so we're going to use our model matrix times our vec4 times our vertex. So our vertex is coming in, if you remember, in local coordinates, and we need to move that vertex out in world coordinates. So we simply multiply by our model matrix, and now this value, this XYZ position, what I'm calling fragment position, it's the position of our incoming vertex, but it's now in world position. If we were to multiply, that's basically the same thing as our GL position, which we won't change. This portion of our GL position is world. When you multiply it times the view, this is in view space, and then if you multiply it by the projection matrix, the final position of this vertex is in normalized device coordinates. But we need, and we still need that for our GL position, but we need to create a value, a vec3 that we can pass to our fragment shader, which is in world position. Now back over to our lighting fragment shader. We need to take in those new values that we're passing from the vertex shader, and those are vec3 normal, frag position. Okay, let's fill out. We're dealing with diffuse now. So now let's create a local variable, normal, called normal, and we're going to normalize our incoming normal just to make sure that it is of length 1. Because if you remember, there's interpolation between vertices. The fragments that are in between vertices, there's interpolation between the vertices themselves, and so we want to make sure that our normal is always of a length of 1. So we need to figure out our light direction, and that is done by normalizing the light position minus the frag position. That's our light position, our light direction. Then, as I talked about, we need to take the dot product, and that's what this variable, I'm calling it n.l, which is normal, the normal vector dotted with the light direction vector. So we're going to take the maximum of the dot product. Let's do this first. I'm going to take the dot product of the normal and the light direction, which we just created. But we have to clamp that. So the way we're going to do that is by wrapping this, passing this into the max function. So we're saying that the maximum value that the dot product can't go negative, so we'll clamp it at 0. So So our n.l will be 0. So our diffuse component is going to be our light color that we're passing in as a uniform times this n.l, which is basically the brightness or the intensity of this color. So this is the intensity and we're multiplying it by whatever color that we're passing in or setting as a uniform. And so our diffuse, don't need this one anymore. Our diffuse component now is this new value. So depending on the angle between the normal and the light, the vector, the direction that the light's hitting that spot on the model, the brightness will vary. So now we have ambient and we have diffuse. Okay, so let me go back to main, make sure I didn't miss anything, and let's go ahead and build, which we shouldn't need to because we've just been modifying the shader, and run F5. And we do have an issue. I probably spelled something wrong, so let's move over here and see what the deal is. So it's not liking our variable called light pos. So I apologize for that. Let's go check it out over here and see what the deal is. Oh, I can see it right away. I left off the important part of actually passing in our light position, light pos. So where'd it go? This right here is a uniform that we're passing in right here. So we're passing in only to our fragment shader. We don't care about our vertex shader. We don't need the light position. We do need our vertex in world space, but so we need to pass in our light. So now that it's coming in as a uniform of Vec3, we need to actually set it over here. So let's set for our lighting shader. Let's copy this line, and we named it light pos, light position, and that is this variable right here. So that's our light position. So that's the thing we're moving around. So we have geometry that is showing us our light, but we need to pass that position into our fragment shader. So I just built, let's run, and it looks like we don't have any errors now. And there we go. So let me back up a little bit so you can see the light. So now we've just added diffuse. So see how the floor is showing the light, the reflection of the light. And we move over here so you can see the face as the light gets near. You can see how it fades in and fades out. So when the light is not anywhere within that 90-degree angle of the face, I'm talking about the face of this crate right here, there is no lighting for diffuse on that face, and it's at that point only ambient. And if we were to, just for grins, change our ambient to something even less, so let's say 0.05, save. So our intensity for our ambient's even smaller now, so it should be even darker. So notice, it's hard to tell, but I can tell it is darker. Okay, so that's diffuse. And notice now our bunny is not flat anymore. As our light's moving around, you can see that our bunny now has some definition to it, has some depth. But things still look pretty matted. You don't see any specular highlights. So let's add those now. To come up with the specular component of the Phong lighting model, we care about the relationship between the view and the reflection vectors rather than the light and the normal vector like we did for the diffuse component. The specular highlight you see as the shiny spot on the smooth object depends on your viewing position relative to the reflection of the light off the surface. Now we calculate the specular component by finding the dot product between the view and reflection vectors. This is similar to finding the dot product for the diffuse component, except we're using different vectors. So it'd be something like this equation. Then we raise the result of the r dot v to some value that we're calling the shininess factor. We're raising it to a power. the shininess factor will dictate how big the shiny spot that you see on the object. So here's an example that I pulled from the web, an image showing different shininess factors. I don't know exactly what the values are, but the smaller the value, the bigger the highlight is. So for the top left image, that could be 0, so there is no visible highlight that you can see. The lower right with the very small highlight, that's a very large number. That could be as high as like 250 or higher. So this is just something you need to play around with. The specular highlight determines how hard and how shiny the object is. All right, so now that we understand specular, let's add that in our code. So we're going to need our view position, and we're going to need a few other things. So for our view, we need to modify our camera actually. So let's open up our camera source and let's make it easy. We're going to create a new function called glm get position, so we can quickly read the position of our camera and pass that. So this is going to be a const. Let's go implement that. So open up the camera class. So this is, notice I'm adding it to the base. So this is like super simple. So watch this. So we're just going to return m position. Oh, it's not, IntelliSense isn't working because I didn't scope it yet. So this is part of our, and I just had mentioned that this is part of our camera base class. So we're going to return m position. There it is. That's simple. So our get position returns our position. So we're going to need that here. So let's create it right here. A new glm vec3 called view pos x equals fps camera get position x, and then we're going to do that 2 more times. Once for y and z, y and z. And we are going to need to pass that to our shader. And we'll need to create a new uniform, obviously. View pos. Okay, so let's add that. Before I forget, I'm going to add our uniform. I've misspelled it twice in a row. So that's our view position. So remember, we have to have the position of our camera, or view position, or our eye position, depending on which website you read. It's named multiple names. Okay, so this is actually going to be our Phong lighting model. Okay, so let's add that shininess factor, the factor that is the thing that we raised to the power of, and let's just make it 100. Now we need a vec3 for our view direction. Let's figure out our direction, and like we've done in the past, we need to normalize the subtraction of two vectors, 2 positions, creates our view position. So our view position minus our frag position, we get our view direction. We need our reflection. Remember, we talked about our reflection direction, and we're going to call a GLSL function called reflect, and we're going to subtract our light direction. Our light direction we calculated right here, so we need our diffuse. We need this calculation. So we need to flip the direction, the opposite, to the opposite, and so that the both vectors are pointing in the same direction. So remember from the drawing, we drew a vector from the light to the surface, but we need it in the same direction as the normal. And the normal comes from the surface and away from the surface, so we need to make sure that those are in the same direction. Okay, so that's our direction vector. Now we need to deal with both of those. So we're going to similarly what we did for the diffuse, we need to come up with a variable I'm calling r.v. So we're dotting our reflection vector with our normal vector, or I'm sorry, view direction. And so this is similar, just using different vectors, view direction. And like we did before, we need to make sure that we take the maximum so that we don't let the dot product become negative. So we're taking the max of the dot product between the reflection vector and the view direction vector. And then we're changing this, so we need to multiply our light color times our, I'm going to call it, I'll make this in a second, our specular factor, that's our intensity factor. And then we need to raise the n dot, r dot v to our shininess value. So our specular factor is something that will get replaced when we talk about materials. This is very similar to our ambient factor. This is the intensity, so it's an artificial setting of our intensity. I'm just going to make it 0.8, so it's not full bright. So our specular highlight isn't completely bright. So now we have our specular written out. Let's test this out. So I'm going to do a build, because we did make changes in our camera and our main, and let's run it. Like before, I have errors. So let me see what's going on here. All right. Undeclared identifier, reflector. I can't spell. So this is, I need a T, reflect with a T. I know it's frustrating if you're following along. Okay, so I'm checking my spelling here. Let's try it again. Okay, it looks like we succeeded there. We don't have any errors. So now we should have our ambient, our diffuse, and our specular highlights. So if you look at our bunny over here, who's our gray bunny, we now can see specular highlights as well as the bowling pin. So now you know why I added the bowling pin and the bunny, because it makes specular and diffuse look cool. So we back up here. Got our light going back and forth. You can see the specular highlight right there for our light. So it's showing up on the floor. And if you can see it, you can also see that our wooden crits are very shiny, and you can see the specular highlight moving across the crates. Okay, so we've just created the Phong lighting model. Now I want to talk briefly about what's called the BlinnPhong lighting model. So let's go ahead and move over to our slide deck, and let's talk about that. Now let's implement what's known as the BlinnPhong shading model. And BlinnPhong is very similar to Phong, except it's been improved. So James F. Blinn improved on the Phong lighting model back in 1977. The Phong model had problems, or has problems, when the angle between the light's reflection and the view direction is greater than 90 degrees. So remember, we're taking the dot, for Phong, we're taking the dot product between the reflection and the viewed vectors. Basically, the specular highlight simply, when this happens, when the angle between those is greater than 90, the specular highlight pretty much just gets cut off at that point. So BlinnPhong, in the BlinnPhong lighting model, he creates what is called a half vector. So the half vector is a unit vector that's halfway between the view vector and the light direction vector. So notice that I've removed the reflection vector because we don't really care about that anymore. So now you can hopefully make out in my image here that the half vector, which is yellow, is halfway between the light direction vector and the view direction vector. And so what happens here is you take the dot product between the half vector and the normal rather than the dot product between the reflection and the view. So the calculation is done basically as it was before. We're just using different vectors as I mentioned. And so the product, the dot product between these two vectors is raised to the shininess factor like we did before. The beauty of this approach is the angle between the half and the normal vectors will never be greater than 90 degrees, even in the worst case. So no matter where the viewer is looking or what angle the light is, the angle between the half vector and the normal vector will never be greater than 90 degrees. So therefore the specular highlight will never get chopped off. Okay, welcome back to the code section. Let's go ahead and implement the BlinnPhong lighting model. So we're not going to need our reflection vector, but we will now add our half vector, and that is going to be our we're going to take the normals out. We're going to normalize the light direction with or plus the view direction as we talked about. Notice that we got rid of the reflect call, that function call. That will save us time in our fragment shader. So this is a little bit more efficient. So now we're going to need, let's just rename this one. So instead of reflect dotted with the view, now we're going to have our normal dotted with H, our half vector. And like we did before, we need to make sure we have we clamp the dot product so that it can't become negative. So our half direction 0. So now we're going to use our n.h instead of our r.v. Our shininess is still the same. Save and run. So now you probably, it's hard to notice a difference. As I talked about, really the only difference, one of the main differences is the specular highlight size is going to be bigger, and so you need to increase the size of our shininess to compensate for that. So it's hard to tell from running this example in this video, but if I were to, not that big, if I were to make it 120 or larger, doubling it is going to, so doubling the shininess factor for BlinnPhong will match the size of the highlight for Phong. Let's just run this again. So I just changed the shininess factor to 120 instead of 100. Not a lot of difference. It's hard to tell, but the BlinnPhong lighting model is what was used in the fixed function pipeline of the older OpenGL. So there we have it. We've just done it ourselves in our own shaders. I said before that lighting involves the object's material and the light's color. The final color of the pixel in the fragment shader is the summation of the three components that make up the light. Color of the ambient, color for diffuse, and color for the specular. To keep things simple, I've just been using a single vec3 to represent the color, but we can do better. A better approximation of light is one where the light is made up of three components, ambient, diffuse, and specular, where each component is an RGB value, a vec3 type, and you can control each of them separately. So for example, you may want a yellow light, which would be the diffuse portion, but with a bluish specular highlight and maybe no ambient. Like lights, materials or objects have materials, and each of the materials is made up of those same three components, ambient, diffuse, and specular. But these represent the reflectivity of the material. And there's also an additional value called the shininess. Now the shininess value was, we used that as the exponent of the result of the dot product between the normal and the half vector. We did that for specular. So very simply, the color pixel value for each of the ambient, diffuse, and specular is simply the multiplication of the material and the light of their respective component. So the ambient color of the material and the light multiplied together becomes the ambient's pixel color. And similarly for diffuse and specular, except with the addition, for diffuse it has the brightness factor, which is the n.l, and for specular it's n.h raised to the shininess. So you take all those three final color values, add them together, and that becomes your final pixel color. So back in our fragment shader, we need to make some changes, but first I want to highlight what we did as more estimations to keep things simple. So as I mentioned earlier, we created a single Vec3 light color that was multiplied by each of the ambient, diffuse, and specular components, and so basically it was just a single component, if you will, probably considered as just diffuse. For the material, we didn't really have materials, so we included this factor that kind of scaled the final pixel color. And however, for the diffuse, we actually did do a texture lookup, but it's located in the global space of our fragment shader. We're going to do better. Now we're going to reorganize our shader to include first a light structure. The light structures can have a position, ambient, diffuse, and specular components. Just like C, GLSL has it supports a structure, and it looks, the syntax is basically the same as in C. So we're going to create a structure, and then we're going to create a uniform variable, in this case called light, and out of that structure. And then we're going to from our application, we're going to set the various fields of the light variable in our application, and then it'll get passed to the shader via this uniform. There's another way to write, just like in C, there's another way to write the variable here, so you can make the whole structure a uniform and declare a variable. Similarly, we're going to need to write a material structure. And the reason why we use structures is just to keep things organized. We could write, taken all those fields and made them separate uniform variables, but it just kind of makes things more organized by combining them into a structure. So again, in the application, we're going to assign the material fields, ambient, diffuse, specular, and shininess, and those will get passed to our shader. But we're going to go one step further. Instead of having a diffuse color, we're going to use our texture map. So we're going to take that texture map that we were writing in global space in our fragment shader, and we're going to put it into our material structure. We could also assign a texture map for the ambient and specular components of the material, but we're not going to do that at this point. We're just going to continue with our diffuse texture map. So back in our fragment shader, let's add what we talked about. So I've already taken the liberty of adding the material and the light structure that we talked about just now. Let's continue modifying this file. So we need a light uniform, and so that gets rid of our light color here. And we also need a material uniform of type material. So we're going to keep our and our light position goes away because position is now included in the light. So the only thing that remains is our view position. All right, so down in the shader, we're going to get rid of this ambient factor because let's deal with the light first. So now we're going to be using the ambient field of our light, and just like the syntax for C, we use the light variable with a lowercase l of type light structure named with the uppercase L. You can name these anything you want. So we're accessing the ambient field of the light structure using the dot operator, and we're multiplying that times the material ambient, and that's up here. So the result is a Vec3 color that ambient that we're using down here. For diffuse, we're not using our global value now. We're using our light's diffuse value, and we're going to multiply that times our material. But the way we're going to do this is we're going to do a texture lookup because our diffuse is a texture map. But we need to make it, where are we? We need to make it a vec3. So I'm going to make it a vec3. Normally they were vec4s. So we're going to take our, do the same thing that we did down here. So basically this. So copy that, put it in here. The result will be, we got to rename our texture map to diffuse map from my texture. So what this will do is it will do a lookup of our texture map using the text chord that we're passing in. Where are you? Right here. And return the correct texel from that map. So we're going to be multiplying our light diffuse times our texel, and multiply that times our brightness factor here. For specular, similarly, we use the specular field. We don't need this specular factor. That was faking our material. Now we're going to use the material's specular directly. Let's save that. Texel, we don't need this anymore, and we don't need the texel here. So it just becomes our ambient plus diffuse plus specular, which are calculated here, and then we set it as a vec4 because that's what a frag color needs to be. And lastly, the shininess is coming from our material. So we're going to, and see if we named it the same. I'm going to copy that, paste it here just in case. Okay, so that the power that we raised to is not this anymore. We're going to be passing it from our application. And I did misspell something, so I might as well catch that now. Light specular, material specular. Did I spell it right up here? Specular, specular. Okay, one last thing as I'm looking over the code. Our light position that we pass in is no longer its own uniform. We need to use light position here. We're passing it in from this structure. Alright, so that looks correct. Let's head back over to our main application and make some changes here. So now we need to pass our light properties and our material properties. Okay, so just kind of organize this a little bit. I'm going to move this back up here. These are the same. I'm going to pull this down a little bit. Okay, so light color is no longer a single value like that, single uniform. Now we're passing it light ambient. And we use the same syntax here as what we're using in here. So light ambient would be light ambient, spelled the same. And let's just make up some colors here, just for the sake of this demonstration. Let's make ambient fairly low level, not too bright. And let's go ahead and copy this a couple more times. This is going to be diffuse. And we're going to go ahead and pass in our light color that we're setting up here. And then for our, let's make this specular. Let's assign a specular highlight of, I don't know, some grayish value. Actually, just just for fun, let's make it yellow. Fairly bright yellow, maybe a little duller yellow, just so we can see a change. And light position, still our light position that we're moving back and forth, so we're passing that through as well, except we now have a structure variable instead, a structure field. Now let's set some properties. So in our loop here, and these could be set differently, but we're just going to hard code shader, wrong one, light shader, set uniform. So we're going to set our material ambient to some value of x3, and let's make it again just like the light, fairly low level, so it's not, doesn't brighten up the scene too much. Let's copy this, do our specular, and we'll come back to our diffuse. Specular, let's make our material reflect our specular highlight maybe halfway. So these values are from 0 to 1. And let's set our shininess value. And this is going to be, let's just make it 32. This is, we need to, actually, notice we're getting a little red squiggly here. We need to modify our shader so that it can pass in a floating point value. Right now we don't have that, so let's go ahead and add that. So open up the shader class, and let's copy one of these and add, actually we're going to need two, and I'll explain. So this first one we'll pass in a GL float. So we've supported Vec2, Vec3, Vec4, or Vec2, 3, 4, and a Mat4. Now we're adding a float. And let's just name it that F. And we need another one, set uniform sampler, because we're going to need one for our texture, passing in our texture. And this will take in a GL int, and we're going to call this slot. This is for our texture slot. Let's copy both of these and open up our shader CPP file. And down here, let's paste both of those. Scope. So let's copy one of these here. Actually, we'll just copy both of them. We'll take this one. Be modifying it in a second. So this is for the float. So we're going to call our internal function get uniform name to see if we can get a location of one that's already been used, or it's already been set, I mean, and we're just going to pass it our float, and this will be a single float. So it's we're calling the GL uniform 1F. So it's taking in, it's the overload, or it's the, not the overload, it's the function that passes in one float, a single float. And for this second one, just take this, copy this. So we'll pass, get the name, and for this, we're going to do the function call for a 1i for an integer type, and we'll pass in our slot. But we also, in addition to this, we want to set our texture. We want to activate our texture. So we'll call the GL active texture. And we did this in our texture our texture class. So this should look familiar. So we're going to set the active texture and also pass the uniform the int to our shader. So if we compile, this should get us going. So back in main, so now we've created both of them. This one passes in a single float, and now we need to do our diffuse. So instead of calling set uniform, we need to call the new one, and we just created set uniform sampler. By the way, did I call it that? Yes, I did. Okay, I was wondering if I called it. For a second there, I thought I called it texture. All right, so in our shader, we named it diffuse map. So that's the name that we need to name here. So diffuse map with a capital M. So we're passing it. So we're setting our uniform called diffuse map to a 0. So our slot is 0. Now, you notice we had not done this before. We never explicitly set the texture slot. And going back to the texture, if you remember when we did the texture tutorial, slot 0 or texture unit 0 in shaders was set by default, so you didn't have to explicitly set it. We're going to go ahead and set it here, even though this line is not necessary because we're only sending one texture to the shader. But if we send multiple textures, like if we did have a spec map, so if the specular was a sampler 2D, then we would have two samplers here, and we would have to explicitly tell the shader which texture applies to what texture unit. So we could say that diffuse map is 0, and so we would say assign that here. But we may, maybe if we did have one, we could say, hey, we have a specular map, and we're going to assign that to texture unit 1, and which may coincide with something like this, where you have two textures. But we're not going to do it that way. But that's just showing you. That's just showing that you could have multiple textures. An advanced class, an advanced tutorial in multiple texturing of shaders, I might do that. But for now, I'm trying to keep this simple. Okay, let's do a build, and let's see if this works. F5 run. And if we have color and lighting, as we do, then it looks like it's working. This is back up here a little bit. Our light, so we did change, we could do that. We could change the other shader that we're using called basic frag and basic vert that we're using for our light bulb there, our floating light bulb. We could make it the same color, but I'm not going to bother. We would basically, what we would do is take in the uniform, create a light structure over there, and take in the uniform for the color and color our little sphere, but we don't need to do that. So notice that the specular highlight on the ground and over here on our little shiny bunny and our bowling pin is yellow, which is what we specified. So where was that? Yeah, the specular. So let's make it white again. That's a 1 1 1 build. And I want to show you something too. Let's so that was a specular, a shininess of 32. Let's make it 5 just to see what happens. So notice this looks more like a pearl, more pearl shaded. The specular highlight's very small, or I'm sorry, very large. So the smaller the specular number, the bigger or the larger the specular highlight is. The bigger the number, the smaller the specular highlight, or the more shiny the object looks. So if we make this 150 and build, okay, let's run it again. So I changed the specular highlight, the shininess factor, to a larger number. So now it's a smaller, notice how it's smaller. And on the ground you can see that it's a smaller circle. Before we end, I want to talk about a potential problem involving normals and scaling. Right now we're passing the normal that comes from the vertex attributes onto the fragment shader. But there's a problem when you scale an object non-uniformly. That means you scale in one or two axes, but not in all three equally. We did that with the floor a few videos back, where I scaled a cube down, smashed it down, and then stretched it out to fit a larger area. So when you scale a model uniformly, the same in all three directions, only the magnitude of the normals change. And we take care of that by normalizing them before we use them in the fragment shader. But when you scale them non-uniformly, it changes their directions. So to fix this, smart math people figured out that you can take the transpose of the inverse model matrix to create a new matrix that we will use to multiply against the incoming normal direction vectors. In code, it looks something like this. So this is what we're doing now. We're just passing the normal on to the fragment shader. So this is what we're going to need to do in our shaders. So we'll do that now. So back in code, let's go ahead and do that. So here's, we're back in our lighting vertex shader, and we're going to go ahead and change this. So we'll add what we saw in the previous slide. We'll create a mat3 matrix. We'll perform a transpose on the inverse of the incoming model matrix. And then we're going to multiply that resulting matrix. This creates a matrix, a mat3, and multiply that against our normal. So our normal is a vec3, and we're multiplying by a 3 by 3, so we're good to go. And the result is a vec3 again, and that's what we're sending out. So save, run. There shouldn't be any changes. This should actually work, but we're not scaling the model. We're not scaling any of the models actually, so we won't be seeing any relevant changes, but just running it again will show us that everything still works. Okay, so there you have it. We've just created a light structure and a material structure, and we've created a single simple light that has a position and color assigned to it, and we've implemented the BlinnPhong shading model for lighting. So now I think what we want to do is talk about the different kinds of light types that are common in scenes, those being directional light, like the sun, where the light is defined by simply a direction, not a position. There's a point light, which is similar to what we have, except the light emanates from a point, just like we're doing, but it dissipates through distance. That's called attenuation. So we should implement that. And we also want to talk about a spotlight, which is used like a flashlight. So, but that will be in the next video. So this video is long enough. That'll do it for now. Appreciate you watching, and hope you join me in the next video.